Our next topic is graphical data presentation, how we present data to people. People commonly present data using graphs and pictograms. There are really two rules of thumb here. First, without proper scaling, a graph tells you nothing. Second, even accurate graphs and pictograms can be misleading in that they can make the data look better or worse by presenting the data in a manner that leads to distorted perceptions, for instance, of spatial relationships. For instance, when you truncate or tear a graph, that graph has an X or Y axis that doesn't start at 0 and increase at a constant pace. These graphs can create the impression of important change where there's relatively little change, or conversely, the impression of relatively little change when there are significant and important changes. In a similar fashion, how you bin your data, how you break up that data, organize it, and/or measure it, your units, can dramatically impact people's perception of the data and relationships that they might or might not see in it. So let's look at some examples that might illustrate this. If we look at this graph, it makes it seem like graduate physics is easy. I mean, look at all the people who are up here by 100 percentile. If I introduce a slightly different scale to that same graph, we realize that that perception of graduate physics being easy was really created by a combination of absent, inconsistent scaling and weird binning. So I started at 0, though I didn't report that. I just reported a generic number of people. And then I went up to 4, which is really a pretty small sample size when you get no indication of that in the original. And I don't keep the relationships, spatial relationships on this axis equal for equal distances between numbers. So I make 4 seem a lot bigger than it would be if I kept it at this scale. Similarly, I bin this data very oddly. I take everybody essentially who passed that physics course, 100 to 65%, and I group them into one data point up here. Then I essentially group everyone else, everybody who didn't pass the class, into these other 2 data points. And really, I go down to 25 so that there is nobody who falls into that 0 to 25 category. Here's another example of how inappropriate or malicious scaling can distort people's perception. So this is a graph that was presented during a House Oversight Committee hearing on Planned Parenthood and what Planned Parenthood was up to and whether or not they deserve funding. When we look at this graph, it runs from 2006 to 2013, and during that time, abortions just seemed to skyrocket. Well, at the same time, cancer screening and prevention services seem to decline dramatically. In fact, they cross each other so that it looks like Planned Parenthood has become a service that primarily focuses on abortion and not on other women's public health services. The first thing that we ought to notice is there is no scale here. And in fact, this is 2 million, and this is essentially 300,000, and this is 935,000, and this is 327,000. So the lines on this graph don't represent objective relationships to one another. A better way of graphing this is as follows. Here we've got our years. We've got our axis here starting at 0 and going up in even intervals of 600,000. When we do that, we see a completely different picture of Planned Parenthood. Essentially, abortions have remained constant during this period of time. There's an increase, but that increase really isn't very large relative to past years. Cancer screening and prevention services do go down, but they don't go down so far as to fall below the level of abortions for any given year. And in fact, experts testified that it was likely that cancer screening and prevention services had gone down because women were increasing their use of IUDs and other birth control devices that require fewer cancer screening. So there was no clear relationship here at all. Whereas this suggests there's some sort of malicious decision to up abortions and down other women's health care services. Here's another example of how when one breaks up the data, when one bins the data, you can change the perception of the data and its relationships. So here are 3 graphs of COVID-19 death data, different news outlets with different bins. Here we've got NPR News. They have data from China. They represent their data with 10-year interval bins. Well, really 9-year interval bins. 0 to 9, 10 to 19, and all the way up to 80, where 80 just takes all the rest of the values. So while this value is high, we don't know if it's 80 to 89 or 90 to 99 or so on. They also choose to represent deaths in terms of percentages of those populations. Since those populations probably aren't equal, those percentages aren't comparable to one another. Now let's look at the Business Insider graph. The Business Insider graph we can immediately see problems with. Their binning is inconsistent. They start off 0 to 19, 19 years. Then 20 to 44, 24 years. Then 45 to 54, 9 years. Then 55 to 64, 9. 65 to 74, 9. 75 to 84, 9. And over 85. Again, we see that particular category, which may include a lot of people who are more than 10 years apart, is much higher here. But the really interesting bump is right here. Right? This is the only graph that shows a bump at this particular kind of age range. And it's troublesome because the binning is inconsistent. We have 20s here, we have 10s here. We start our 10s at 54 and then start going up in these odd sequences, 55 to 64, 65 to 74. This sort of suggests that this was grouped with the numbers in mind. Finally, we have deaths in Italy from COVID-19 by age group. Here again, we have some unusual binning. We start off 0 to 29. Then we go to 10-year intervals, approximately. We are given this number here. We can assume that it's numbers of individuals, but we're not really told for sure. This graph came from the BBC. So how you bin things, the units you choose, the groups that you make can dramatically affect things. And they can provide people with misleading perceptions of the data and its relationship to other bits of the data. Pictograms and bar graphs shouldn't be scaled uniformly as a general rule, because this creates a perceptually misleading comparison between the different pictograms or bar graphs. People tend to focus on area as opposed to height or width in a single dimension, and so uniformly scaled pictograms make a difference appear to be much larger because the volume increases much more when you uniformly scale them. That is, increase both their length and their width. So here's an example that I cooked up. like Wallace versus dislike Wallace. Now, we don't have any idea what the actual numbers are, but here's how I drew this. I took an imaginary number here, represented by the radius and the width, and then I created a doubling of that, where I doubled the radius and I doubled the height. This, in effect, created an enormous increase in the volume, giving the consumer of this data the impression that I'm really popular. Many more people like me because that volume for that cylinder is so much bigger than the volume for the dislike cylinder. One final one here. This is a pictogram, a pie chart. Pie charts can prove deceptive when the quantities aren't proportional in the chart or they exceed 100%. Now, this was a Fox News pie chart from the 2012 presidential run. If you don't pay attention to these numbers here, you might not notice that apparently somewhere around 193% of people are backing presidential candidates in the primary in 2012. So clearly, these numbers can't actually be indicative of the numbers or the percentage of people who really back these individuals. A pie chart should always add to 100%.